On behalf of Applied Materials, I wanted to thank everyone for the invitation to this conference. The title of my talk, actually, I adjusted a little bit, is Materials Engineering for AI Compute. And I wanted to use this opportunity to also initially introduce Applied Materials to this community and also describe our viewpoint and how we're looking at this. And we're coming from a different portion, very different community, and we are more on the materials side and materials engineering side. So Applied Materials, just a brief intro, is a long history, 50 years. In essence, we've been providing the systems and tools that are used for manufacturing, for both in the semiconductor side and the display side. One of the areas that Applied does pride itself on is innovation. So it does continue to invest heavily, and we do feel that in this new AI era, that maybe there's reason for new interconnectivity, new partnerships, and new methodologies by which we can also link from a materials to systems kind of view to complement others, this common paradigm of materials to software or materials to applications. In essence, all this kind of dialogue, and also from the previous speaker, we need to connect the various communities, and this way we can actually push the field forward. So historically, Applied Materials has focused on, for example, a more singular step, a discrete step in a representation of its materials engineering in a process step in a tool infrastructure. Over the years, it has developed multiplicities of infrastructure that allows us to deposit, manipulate, modify the films. And over time, as we've basically kept cadence with the Moore's Law, we have created integrated materials platforms that help, in cooperation with our customers and partners, certain select integration steps in the traditional CMOS scaling. But as we look forward in AI side, say in the materials and device types, there is a certain immaturity in the usage of certain novel device types, as been discussed over this conference. Memristors is but one format, but even memristors is quite broad. Even from a ReRAM or memristor resistive base, there are many different classes, and they really need to be engineered. So what we think is, as we go forward, in terms of this notion of software-hardware co-optimization, which is kind of broad, high-level term, we'd like to see whether we can help enable a faster connection between the fundamental materials innovation and a potential AI performance. And through this fashion, this is somewhat of a simplification. We want to see whereby we can help the community in this kind of materials to systems view of this type of cooperation. So, from Applied Materials viewpoint, as we move from this kind of PC internet era to the mobile, this growth is large. This is commonly described, but what could we practically do, right? We need to segment this problem and create tangible points that one can leverage to then add value and push the field forward. So this is kind of the high-level thing. So what we see from Applied's vantage point is that general performance are slowing. So folks are familiar with this. From a Moore's Law's point of view, it's actually been quite remarkable, right? If you look at last 4 years and just do some math, it's actually been quite sustainable, and it's remarkable, about 2x every 2 years. But in recent years, things are becoming more and more challenging. And that's because it's not just the notion of shrinking or materials, it's a combination of many effects, right? There's some notions of power performance area and also cost, but really cost could be a larger component. But the other kind of thing that's happening is that if you look at it, aside from Moore's law, there's the use of parallelism or even just feature scaling. All these things, every single knob has value, but it really needs to be all deployed in a unified fashion. And the consequence of this is, from our viewpoint, the nodes are taking longer to deploy one generation to another. And this affects the building blocks that are used for the AI compute. So this is a little bit of a cartoon. The other dynamic we see is that there's a rapidly evolving architecture because of this data explosion. There's a notion of hard iron, right? Deploy the GPU for training. There's all variety of approaches to do, GPU strong or CPU or mixed mode, and there's also a variety of other forms of accelerators, TPUs, in some ways even, you can think of it XPUs. And there's also the need for heterogeneous integration of some form. And these all vary from the data center to the edge, inference versus training. But even in the edge, it's complicated. There's the class, overall class areas such as auto and mobile phones, but then there's also the far edge. So all of these things are happening at the same time, and there's a notion of customization, but all of these things, in some ways, we view that there's a targeted workload, and there needs to be a materials to systems kind of view to help address that targeted workload, but it needs a certain level of flexibility, obviously, so that it can become scalable. If you design something very, very specialized, it could be very suited for that one use case, but if you'd have to redo the cycle again and again, then that also not necessarily solves this kind of speed up issue. So from this kind of mindset, this is a adaptation from our CEO, Gary Dickerson, gave a talk in last year's AI Design Forum that was given by Gary. We feel that a new playbook is needed for this connectivity and speed to really address this kind of a backdrop of challenges of increasing complexity, integration, and time to market. So even if there's a demonstratable device type that looks promising, it not necessarily is facile to integrate it into a certain flow and also deploy the manufacturing infrastructure to make it controllable, repeatable, and all sorts of that kind of issue. It's just as important. So in some sense, if we borrow this critique of this serial nature of computation versus a more neuromorphic, we feel that within the overall community, this is just representative and not necessarily mean to show full logical sequence, but there's the design, EDA, materials, equipment, integration, manufacturing, all sorts. Instead of a serial handoff, we believe a more connected mindset may be of more utility, and that's what we need to move towards. And that's why we're interested in kind of partaking in this community as well. And we believe this connectivity is needed to accelerate innovation. And from Applied's point of view, then, as a base level, many of these innovations, even in existing CMOS and existing kind of a support of, relentless classification of data as a means of deep learning, and even future in neural, there is a materials element. There is also continuous need to enable shrinking, which doesn't stop, packaging, structures, and architectures. This is where, this is how Applied views this changing environment. So how does this relate to what we see in the AI side? So this figure on the right is the adaptation from some of the Bill Daly's work from NVIDIA. We see that there's a lot of data, and there's a lot of the models are getting very larger. There are different ways to tackle that, right? You can change the algorithm, you can prune, you can do sparsity, you can quantize, you can do all kinds of things. But right now, while those issues are being resolved, there is also we don't necessarily see that from the practical use cases, the ability to hold larger models and also to be able to crunch that really is driving the industry. But one challenge, as cited by many, is that as you do this, general power is not necessarily useful. This TOPS per watt becomes an issue. Also, in the edge, a per millimeter squared also matters. But this is also within a chip level, but then there's a notion of the system and the end applications level. So we believe that additionally, besides algorithm hardware co-design or software algorithm co-design, right, there's a general trend to move the memory closer to computation. There's a need of using emerging memories for even on-die storage of weights. And then there's a need to move towards more in-memory compute and so-called analog compute. And there's also future compute paradigms such as quantum and neuromorphic, more spike-based. So from this, even in this kind of challenging environment, this broad field, this is kind of a simplistic framework that we've adopted to take a look at this. What it's trying to represent in a simplified format is in this first era, most of the work is in accelerators. There's an importance of DRAM. It's costly, but it's utilized with HBM, packaging, bringing the memory closer. The horizontal is meant to say that we don't see these things disappearing. All new innovations should be accretive to the base infrastructure we also see it as a function of errors. That's the better way to, instead of a calendar time. As we move from this era one of these accelerators, we do see emergence of embedded memories. Memories itself has its own taxonomy and diversity. Many of these memory types were used for historically looked at even for standalone memory or storage class memory. Even within embedded, it has its own constraints, its own specs that it should meet. As you move to analog compute, memristors or ReRAM, FEFET, PCM, NOR flash, there are many versions of this. It was given in the previous days talks. Some of these things could be used to do an analog Mac as one form of speed up. But we also see that, for example, certain folks looking at, say, NOR, that's a available technology, but as you attempt to scale to smaller nodes to match with CMOS, that poses certain challenges because that's very expensive and many mask steps. So how do we bridge these type of gaps? And in the era 3, there's this quantum and also more brain-inspired. So this is a kind of framework. But all of these things, what we see as an implication is that there really needs to be connectivity across the ecosystem. We don't we're not saying that we're here to, solve every single problem. That makes no sense. But we're here to say that we like to support these endeavors, and we feel this kind of community aspect matters, even to the research community as well. From this, we believe that there should be an acceleration of learning cycles and enable a better true embodiment of co-optimization and ability to customize, extending even down to the materials level. So the other thing that we think of is that from a practical building block, there is a physical aspect from novel material synthesis. That what I mean by that is even before a process goes into it, even while you develop a unit process, there could be precursors, for example, chemical means of depositing and formulating a material, all the way to device elements, circuits, test chips, and systems level. But there should be a mating simulation aspect. These things should move in paired fashion. In order to engineer a device, we need to understand from the materials feeding in and also the physics of that device in order to exploit it, to get the output response, right? If there's desired symmetry and linearity, we need to exploit that physics. We need to control it. I'll give you a little bit of example later. So this is the type of framework we think is important as well. And we're obviously more focused on the left side of it, but we need to connect with the rest of the ecosystem. And with the feed forward, feed backward, it is then possible to even do certain virtual simulation to then speed up the physical runs. Because all physical experiments, as you move towards the right, are more costly and more time consuming, but the data is more richer, but we need a tiered screening approach. Whoop, sorry. So from that kind of idea, we also see that we need to help facilitate this kind of lab to fab concept. And this is partly why Applied Materials actually made a very significant investment at the Meta Center here, which is a materials engineering technology accelerator. And this also, in our viewpoint, should encompass leading research groups out of universities or research labs. We also have partnership with larger companies and even startups as well. And they may fall in different areas of the time sequence. But at the end, the ecosystem has to be mated all the way down to the infrastructure and even the maturity of the material supply in order to actually render it and make it available so that it can drive more usage and demand. So one thing, we give an example, this is familiar folks, but what we see is that in conventional neural nets, a lot of it that's referenced, the more typical ones, these are a lot of weights and there's a lot of max. And this is one of the papers from the Google side, a typical usage side. So one that was talked about previously is how do we take this is a simple cartoon, how do we take this sum current means of representing that matrix multiplication, how do we actually do that? This is very simple. You can have demonstrations at very small array sizes. If you try to rely on the materials only, it may not be sufficient because you need to regulate its properties. So you may introduce transistors. As you scale up, there will be peripheral circuitry which demand more area. So this is actually a very large problem set. So, but high level, how would you store a certain number of weights on die, and how could you make this more efficient? We do think this is the methodologies. And this application really needs to be baked in all the way down to the materials level. Even as simplistic as well, not simplistic, but say a certain use case requires 4-bit precision, that has certain constraints on the cell element, and that then has constraints on its materials properties, and so on and so forth. So in this way, for example, this is an adaptation from Shiming Yu's work. This tries to illustrate in a benchmark fashion what is published or what is known of certain material system, resistive systems, PCM, FERAM. There's many more others. Each one, what we highlight in red, is some aspect of it is unattractive in a simplistic side. There's a certain number of states, right? The linearity, the average on resistance that not only tracks to the states, but how dense you can make it in the node, the dynamic range. There are many, many issues, and they do affect in a simple MNIST comparable, in a simple few layers deep net, a apparent accuracy, right? So these are the types of things that we believe we can help on. Additionally, that'll just be from an experimental point of view. So we also believe that key to this is understanding the materials physics. And this is kind of a cartoon of a multi-physics platform capability. So we've invested in this. This is out of literature, but these are experimental, typical memory base. It's a very discretized change in state. This is a model representation. So filamentary, it's gonna either enable sudden jump in current. You can think of it as a variable tunnel oxide in some ways. Or you can engineer these materials so that it's more softer, more gradual, more aerial-like, and get a more, V-like curve. So this is just one that moves vacancies and small perturbations in diffusion. There are other versions that are more electronic-based that maybe fundamentally has advantages, but even to enable that kind of mechanism, a lot of them are based on metal oxide systems. So these other detrimental modalities of conduction must be eliminated for one to kind of mature the device type. To give you an example, the type of partnerships is this one on the left has been announced is that we are working with DARPA, a fabless company, ARM, and also startup Symmetrics to look at core electron RAM. And this is one that does not require movement of species. Additionally, Applied has announced that we have teamed up, for example, with Spin Memory to basically look at MRAM for embedded solutions, but this MRAM could also be adapted in future modifications for AI applications. I mentioned that we've invested in Meta Center at the SUNY and also with Empire State Development. And also we're very happy and proud to have joined the IBM AI Center. And in some ways, I just leave you with this graphic that we believe that in this kind of cooperation and greater connectivity, then maybe we can push this field forward. Thank you.